This video is all about sigma notation. This is a concise and precise way of explaining long sums. We study some examples and some special cases, and then we'll derive some general results. But first, let us look at these. In maths, we have to sometimes sum a number of terms in a sequence, like these two. The first one, 1 plus 2 plus 3 plus 4 plus 5, it's the sum of the first 5 whole numbers. The second one, 1 plus 4 plus 9 plus 16 plus 25 plus 36, it's the sum of the first 6 square numbers. Now, if we had a general sequence of numbers, such as this, U1, U2, U3, and so on, we could write the sum as S equal U1 plus U2 plus U3, and so on. Now this sum goes on and on and on. But if we want to sum n terms, then we can write that the sum for n terms equals U1 plus U2 plus U3 up to UN. And those are n terms. Now we can use the sigma notation to write this more concisely. And sigma comes from the Greek capital letter, which corresponds to the S in sum. And it looks like this. Sigma. And if we want to express this sum using sigma notation, we take the general term UR, and we say that we are summing all terms like UR from R equal 1 to N. And that equals our sum Sn, which is written above. But more generally, we might take values of R starting at any point rather than just at 1 and finishing at N. So we can write sigma from R equal A to B of UR, and that means the sum of all the terms like UR starting with R equal A to R equal B. A is the lower limit and B is the upper limit. Now what I'd like to do is explore some examples using the sigma notation. So take for example this one. It's sigma of R cubed with R starting R equal 1 and ending with R equal 4. So the lower limit is R equal 1 and the upper limit is R equal 4. Well, all we have to do is just expand it out and write it as a long sum, using the values R equal 1, 2, 3, and ending at R equal 4. When R is 1, R cubed is 1 cubed. R equal 2, 2 cubed. R equal 3, 3 cubed. And R equal 4, 4 cubed. And we can just work these out and add them together. 1 cubed is 1, 2 cubed is 8, 3 cubed is 3 times 3 times 3, so that's 9 3s is 27. 4 cubed is 4 times 4, which is 16, times by 4, which is 64. And when we add all of those together, you get a lovely answer, 100. What about this one? It's similar. But instead of using R as the variable, you can use N. In fact, you can use any variable that you want. And in this case, we're summing terms like N squared from N starting from 2 to 5, going up in increments of 1. So starting with N equal 2, N squared is 2 squared, plus N equal 3, 3 squared. N equal 4, 4 squared, and finishing with N equal 5, 5 squared. And all we have to do now is square these out and add them together. 2 squared is 4, 3 squared is 9, 4 squared is 16, and 5 squared is 25. And we can add these very simply. 4 and 16 is 20, 9 and 25 is 34, 20 and 34 is 54. What could be simpler? Look at these two, written using the sigma notation. Just slightly different from the previous ones. Remember, we look at all the terms, such as 2 to the k, and we substitute in the values for k in increments of 1, starting with 0, going up to 5. So the first one, 2 to the k, when k is 0, is 2 to the 0. Then we add 2 to the 1, plus 2 to the 2, plus 2 to the 3, plus 2 to the 4, plus 2 to the 5. Notice we've got 6 terms. And the reason why we've got 6 terms is we started k at 0 and not at 1. And then we evaluate those. 2 to the 0, 1, plus 2, plus 4, plus 3, 2 to the cubed, which is 8, plus 2 to the 4, 16, plus 2 to the 5, 32. And when we add those up, 1 plus 2 is 3, 4 is 7, 15, 31, and then 63. Now look at this one. A little bit more involved, but quite straightforward if you follow the same steps that we've done before. We take the general term here and we substitute in values looking at where it starts from and where it ends. So r equals 1 is the lower limit. So we look at our general term and substitute in r equal 1 first. And that will give us 1 times by 2 times by a half. Added to. Now we substitute r equal 2 for the next one. So that's 2, r plus 1 is 3, plus a half on r equals 3. 3 plus 1 is 4, plus a half on, and I've forgotten my r, but my r in this case is 4. Then we add 1 to it, which is 5, and continue on in the same vein until we get to our upper limit, r equals 6. So that's a half, 6 times by 7. And we can evaluate this out, but we can do a lot of cancelling on the way before we do any of the adding. 2 cancels with the 2 here and here. 2 cancels with the 4 to give us 2 here. 2 cancels with this 4 to give us 2. 2 cancels with this 6 to give us 3. And 2 cancels with this 6 to give us 3. And then we evaluate out adding together the terms. So this one is 1 plus, and we're left with 1 times 3, which is 3, plus 1 times 3 times 2, which is 6, plus 2 times 5, which is 10, plus 3 times 5, which is 15, and the last one, 21. Now, if you look at these numbers, these are quite special numbers. There's a name given to them. They are the triangular numbers. And you should be able to recognise these the same way as you would recognise square numbers or prime numbers or odd or even numbers. And finally, what we'd like to do is just add these all together. 1 plus 3 plus 6 is 10, plus 10 is 20. 20 plus 15, 35, 36, and then add the 20 is 56. So we get the sum 56. Now what about this? We've got our general term 2 to the k, and we want to start with k equal 1 to k equal n. If we write it out, substituting in our values for k, starting with k equal 1, our first term will be 2 to the 1, plus then k is 2. So it'll be 2 to the 2 plus 2 to the 3 plus 2 to the 4, and so on until we get to 2 to the n. Now we can't evaluate this to a finite number because at this stage we don't know what n is. And what if we have these two expressions? We're still using the sigma notation, but in this case our general term involves a negative sign in both cases. So we'll just take a little bit of time and carefully work them out, because it's dead easy to go wrong in these sorts of ones. So take a little bit of time and you will hopefully work them out okay, using the same steps that we've done before. In this particular example, our general term is -1 raised to the power of r, and r equals 1 to 4. So the first term will be -1 raised to the power of 1 plus -1 raised to the power of 2 plus -1 raised to the power of 3, and finally -1 raised to the power of 4. And then all we have to do is multiply these out, making sure that we get our signs correct. -1 raised to the power of 1 is -1. -1 raised to the power of 2, that's squared, is +1. -1 cubed, that will give -1. And -1 to the power of 4, that will give +1. So in fact, our sum works out to be 0. -1 plus 1, 0, plus -1 plus 1, 0. Quite a surprising fact, in fact. Now look at this one. Again, take care. Our general term is -1 over k squared. And we have to use values of k from 1 to 3. So we start with k equal 1. That's -1 over 1 squared plus -1 over 2 squared plus -1 over 3 squared. And then again, taking care with the negative signs, square these values out. -1 over 1 is -1. Squared will give us 1. Plus -1 over 2, all squared, that will be positive, and it's a half times a half, which is a quarter. Then added to -1 over 3 squared. Again, that's going to be positive, and it's going to be 1 over 3 times 1 over 3, which is 1 over 9. We can add these together, adding the two fractions together. The common denominator is 36, and it will be 9 plus 4, and you've got your 1 there. So my final answer is 1 and 13 over 36. Quite a grotty answer, but we've been able to work out what seemed to be quite a complicated sigma notation sum, and we've finally got an answer. But what if we had a long sum and we wanted to write it in sigma notation? How would we do it? Well, why don't we first look at the two sums that we started off with. The first one was 1 plus 2 plus 3 plus 4 plus 5. This one's quite an easy one to start off with because it's the sum of what type of terms? Well, it's a dead easy term because they're adding one on each time. So if we take the general term to be k, k starts with the lower limit 1 and ends with the upper limit 5. So there's no problem with this one. This is very straightforward. But look at the second one. Again, it's not too bad because we notice, and we said before, that these are square numbers. So we could actually rewrite these as 1 squared plus 2 squared plus 3 squared plus 4 squared, 5 squared, and 6 squared. Once we've done this, our sigma notation sum is dead easy, because we can easily see our general term must be k squared. And k must start with k equal 1 to k equals 6. But what about these ones? This is a long sum. What's different about this? It's got fractions, and it also has alternating signs. Negative, positive, negative, positive, negative, positive, and so on. Now the trick in this case is to rewrite all of these in terms of fractions, and then use -1 to a power. So if we look at this, we can rewrite this as -1 over 1 plus a half minus 1 over 3 plus a quarter plus, and so on, to 1 over 100. Now we have to deal with the signs alternating. And if we think back, we did have signs alternating before, and that's to do with negative numbers. Now we don't want to change the value of the fraction, we just want to change the sign. So if I rewrite this as -1 times by 1 over 1 plus -1 to the power of 2, 1 over 2, plus -1 to the power of 3, 1 over 3, plus -1 to the power of 4, 1 over 4, down to plus -1 to the 100, 1 over 100. Have we got the same sum? Well, yes, because look at each term. -1 times 1 over 1 is -1 over 1. -1 squared will be +1 times a half, which will give us our plus a half. -1 cubed will be -1 times by a third, which is -1/3. So that's where we get the -1/3. -1 to the power of 4 is +1 times by a quarter, gives us our plus 1 over 4. So rewriting our sequence that we started off with here into this format, that then helps us to write it in sigma notation, because we can easily see that this is sigma. We know it's -1 to a power, and the power is always the number underneath the fraction. So we'll say that our fraction is 1 over k, because we start with k equal 1, and we raise -1 to the power of k. And to complete our sigma notation for this long sum, we start with the lower limit of k equal 1, and the upper limit k equal 100. So you can easily see that this notation is very concise and a really lovely way of writing that big long sum. Now I'd like to move on to some special cases using sigma notation. The first special case is when you have to sum a constant, like this. If we have sigma of 3 from k equal 1 to 5, what does that actually mean? Well, we work it out. We take each term for k equal 1 up to k equal 5. Each term remains the same, no matter whether k equals 1, k equals 2, k equals 3, 4, or 5. So we actually just get the sum of 5 threes. which is 15. So we have 5 terms. It's 5 times the constant to make 15. So we can get a general result from that. If instead of 3 we have a constant c, and we take our k from 1 to n, what does this work out to be? Well, we do it in the same way. We work out our sum using k equal 1, 2, 3, and so on up to k equal n, and evaluate it. So k equal 1 is c, k equal 2, c, and so on, up to the last c, such that we have n terms. Because we've got n lots of c, this sum can be simplified dead easily to n times c. So this is a general result which is very useful when using sigma notation. If you have to sum a constant from k equal 1 to n, then the value is, and it is a finite value, n times by c. What could be easier? But what about this? What if you had to sum a variable like this, 3k? Can this be written more easily? Well, we'll take this particular example. 3k sum for k equal 1 to 4. So we'll sub in k equal 1 first, then k equal 2, then k equal 3, and then k equal 4. And we get that sum. We notice that 3 is a factor of each one of these terms. So we factorise out by our 3, and we get 3 bracket 1 plus 2 plus 3 plus 4. Now that is equal to 3 times by, if you want to add these all together, that's 3, 6, 10. So the answer is actually 30. Now I'm not so much interested in the answer, but in the process. At any one stage, can you spot something that we know already? Well, look at this second line. You've got 3 times by 1 plus 2 plus 3 plus 4. That's the addition of k when k is 1, 2, 3, and 4. And we can rewrite this using sigma notation. That is 3 sigma of all values k from k equals 1 to 4. So our expression that we started off with, sigma of 3k equals 1 to, for k equals 1 to 4, equals 3 times sigma of k from k equal 1 to 4. So effectively we've taken out, we've factorised that 3 from our first expression, and we've brought it outside the sigma notation. So more generally, we can take that if we've got the sigma of ck from k equals 1 to n, what will that equal? Well, quite easy. All we have to do is that we see that that is c times 1 plus c times 2 plus c times 3 right up to c times n. We've got n terms here. We can factorise by the c, and we get 1 plus 2 plus 3 plus up to n. And then we can rewrite this using sigma notation. That is c sigma of k from k equals 1 to n. And as I say, quite straightforward. When you've got a sigma of c times a variable, c being a constant, you can take the constant outside the sigma notation and you're left with c times by the sigma of k from k equal 1 to n. That's another very useful result that you should remember when using sigma notation. But what if we had this expression, the sum of the variable k plus 2, where k takes the lower limit 1 to 4. What does that work out to be? Can we write it more concisely and easily? Well, we do it stage by stage, step by step, putting in values for k from k equal 1 to 4. So the first term, k is 1, so it's 1 plus 2. Plus, second term, k equals 2, so that's 2 plus 2. The third term is 3 plus 2. And the fourth term is 4 plus 2. Now what I want to do next is rearrange these values. If I rearrange such that I have the addition of 1 plus 2 plus 3 plus 4 first, and then see what we've got left. We've got add 2 4 times. So that is 4 times 2. And then we can easily evaluate this expression. 1 plus 2 plus 3 plus 4 is 10, plus 4 2s are 8. So the answer is 18. But as I said before, we're not so much concerned with the answer, but in the process. Can we look and see at any line, can we use the sigma notation more easily? Well, if we look at this line, we've seen part of this before. 1 plus 2 plus 3 plus 4 can be written more easily using sigma notation as sigma k from k equals 1 to 4 plus, then we've got 4 times 2. So, looking back at what we started with, we've got sigma of k plus 2 from k equals 1 to 4, and it's expanded out to this sigma notation, sigma of k on its own from k equal 1 to 4, plus 4 times 2, where 2 is the constant that was added to the k. So we can generalize this result. If we had sigma of g of k, a function of k, plus a constant c as our variable, and we want to take k from 1 to n, we can use the pattern that we spotted here to write this out using sigma notation plus some other value. The first part is sigma of the function that we started off with in our variable, and the function is g of k. And we see that it should be from k to the upper limit, from k equal 1 to k equal the upper limit. In this case it's 4, but in our general case it's k equal n. So it's k equal 1 to n. Plus, now the next part, remember, it was the upper limit, or the number of terms, times by the constant that you've had in your variable. Well, look here, our constant is c, and our upper variable is n. So it's n times c. So this sigma notation can be expanded to sigma g of k from k equal 1 to n plus n times c. And we can even generalize further using previous results. If we took sigma from k equals 1 to n of a g of k plus c as our variable, we can expand that out, looking at this term first and then dealing with the constant. Now this term is a multiple a constant times by your g of k. So we can bring that outside the sigma notation and say it's a times by sigma g of k from k equals 1 to n plus just what's left to deal with the c, and we know when that's inside the bracket, when we expand it out, we're left with n times c. What could be easier? All right? But what if we wanted to use sigma notation and the variable we wanted to add together is k plus k squared, i.e. two functions of k? What would we get when we write out this long sum? Start simply by substituting in for k. K is 1 to begin with, so the first term is 1 plus 1 squared. Second term is 2 plus 2 squared. Third term is 3 plus 3 squared. And that's our final term, because the upper limit for k is 3. Now we'll rearrange the way we did before to make our work easier. We'll take the 1 plus 2 plus 3 together. And then we'll take the 1 squared and the 2 squared and the 3 squared, the bits that are left. And you can see why I've done that, because here we're adding our constant k's, and here we're adding our k squareds. When we add these together, we just add them up and multiply out using the square sign. You get 1 plus 2 plus 3 is 6. 1 squared is 1. 2 squared is 4. 3 squared is 9. Add that together, that gives you 14. 6 plus 14 is 20. But look at this second line. We can simplify this second line using sigma notation, and it's using sigma notation that we've done before. 1 plus 2 plus 3 is the same as sigma of k from k equals 1 to 3 plus 1 squared plus 2 squared plus 3 squared. That's dead easy. It's the sum of all variables k squared from k equals 1 to 3. Now look at what we'd started and look what we've got. We have broken this sigma notation up into two sums, two sigma sums. So here we've got the sigma of a variable plus another variable, and we've split it up to sigma of one variable added to the sigma of the other variable. We've used the distributive law. So to write this more generally, we can say that the sum of a function of k added to another function of k from k equals 1 to n must equal the sum, two separate sums, the sum of g of k from k equals 1 to n plus sigma f of k from k equals 1 to n. And in fact, we could continue this on. If we added on other functions within our variable here, then all we have to do is add on another sigma of that particular function. Finally, here's a real-life example using sigma notation. Take, for example, if we want to find the mean of a set of numbers. They could be the marks in a test. If we want to find the mean, what we want to do is we have to work out the total sum divided by the number of values. And that's what the mean is. Well, that's actually what we've been doing in the previous examples. We have been finding the total sum, and we have been looking at the number of values. So if I take this example, just say we had the marks 2, 3, 4, 5, 6, and we wanted to find the mean of those marks. The mean will equal 2 plus 3 plus 4 plus 5 plus 6, and we'd have to divide it by the number of values, which is 5. When we work that out, that is 5 plus 5 is 10, another 10, that's 20 over 5, which works out to be the value 4. But more generally, if we've got a set of marks, say xi, we can write the mean in terms of sigma notation. It's the total sum of all the marks, such as xi, from I equals 1 to n, and then we want to divide it by the number of values. Now we know there are n marks, so we want to pi by 1 over n. So the mean is equal to 1 over n sigma x of I from I equal 1 to n.